yeah, I have them. I have kept them somewhere. I'm going to upload them. I will just find some time and then I will upload them on Google Drive and then I will give you the link.
Okay.
So that's it for CAP-C1 and CAP-C2. It's so funny. This problem was so easy, but last time I was like, no, I don't know what's happening here. Yeah. Okay, so let's do this example, and maybe we can try to do it without looking, even though I have already looked. I've looked at this for the first step.
Okay.
So let
But
me
I
just
didn't.
open up like a page, then we can do it there.
I didn't write the example.
Mm-hmm. So we are going to write it in a moment.
Mm-hmm.
So I'll open a blank page. I can have as many as I want. So first of all, the formula. This is like some extension of Cauchy's integral formula.
How I understand, we need this formula to
Yeah, we need
find
this
when
formula.
we have more derivatives in our example.
Yeah, we need this formula to find the integrals when the pole is not simple. For example, in this case, this is a pole of order 3. Right?
Could you remind me what poles means very quick?
So a pole,
if we touch this.
So a pole is a point where the function will not be defined.
Okay, right? But
yeah.
Why he said that this is a power? This is a z0 is our order of pole, right?
No, z0 is not the order of the pole. The power is the order of the pole. For example, look, z0 in this case, it's 3. The power is also 3. This is just a coincidence. And I can see the same coincidence down here. So this is just a coincidence. The order of the pole is the power of that denominator. Yeah. Okay, so we're going to write the formula. Fn z0.
I have this one. Fn z0 equals n factorial over 2 pi I integral Cauchy formula, integral of contour C f of z over z minus z0 f of z over z minus z0 in power n plus 1.
Or n plus 1 dz.
Dz, right.
And here we want to do this integral. We want to integrate
f of z over oh, z example you're saying. Okay, z for
so z4
z square plus 3 power 3
z squared plus
z square plus 3 in power 3
powered by 3.
Powered by 3.
Yeah. Okay. From this formula, the formula we see above, we can conclude that the integral f of z
z4
z
over
minus z0. I'm rewriting this formula above.
Oh, okay, yeah.
N plus 1 dz. It's going to be equal to 2 pi I divided
over
by n factorial, the nth derivative of z0. And we are integrating this along the complex contour. So the first step, if we think about this, you can see that this is going to be equal to the integral z to the power of 4 z
square
plus
3
I square root of 3. So I'm just splitting the z squared plus 3. And then you have z minus I. So z
square root over 3.
minus I square root of 3. And both
everything
of these,
power of 3.
they're going to be poles of order 3. Right?
Okay.
So this is the integral that we need to find. So if you were to think of this, if you draw a complex plane, it's going to have poles at I root 3 somewhere here. It's going to have a pole at I root 3 here. And it's going to have another pole at negative I root 3. And we want to find the integral around the whole region. So we are going to do the integral around the first curve that I'm calling C1. And we will also do the integral around the second curve, which I'm calling C2. Okay. At C1, the simple pole is I root 3. And then at C2, the simple pole is negative I root 3, right? So let's do this integral. So we are going to have integral around C1. The pole is I root 3. So I'm going to have Z minus
Z4. No, we don't need the Z4.
Yeah, I'm going to write the Z4 later. So this is Z. The pole is I root 3, right?
Yes.
And it's a pole of order 3.
3.
And then I will write Z4 to the power 4 over Z plus I root 3 cubic.
Okay.
dz. So that's how we are going to integrate this function. So you see my fz, I have created a new fz at the top. I only have my pole as the denominator.
Okay.
And according to Cauchy's formula, this is going to be equal to
2 pi I
2 pi I
fz fi square root 3
divided
negative.
by n is.
Why are you dividing it?
N is going to be 2. It's 2 pi I divided by n factorial. So it's 2 pi I divided by 2 factorial, because you see n plus 1 is 3, so n is 2. And then this is going to be the second derivative of z naught, right? So let's find the second derivative. F of z is the numerator, right? So
yes,
f of z in this case, it's going to be z to the power 4 divided by z
plus I square root 3
square root 3
cubic,
which is the same as z to the power of 4, and then we have z plus I square root of 3 negative 3. So the f prime of z
is 4z cubic.
It's going to be 4z cubic. And then we have
times negative 3
z plus I root 3 powered by negative 3. And then we add, we keep the z power 4. Yes. And then we now find
negative
the derivative.
3 negative 3 times
z plus I root 3
z plus I root
powered
3
by negative 4
to 4.
Yeah. Okay.
Second derivative of z.
So we now look for the second derivative. Can
It's
we try
12.
simplifying this?
We can take z plus I square root 3 in powered by my negative 3 and just cancel it. And work with only, oh, we can also take the, no, we can't do it.
Okay, we can just proceed to the second derivative.
12z square.
Or maybe we could use the, are you familiar with the quotient rule?
With what?
The quotient, we call it the quotient rule for derivatives.
Yes, yes.
I don't know which one will be the easiest. So the quotient rule says that, yeah, I think it's going to be more or less the same thing. It's not going to be any easier. So, okay.
We need to do it to v square.
Yeah. So let's,
it will be the same actually, almost the same.
Okay.
A little bit complicated, more complicated.
So it means okay, let's see. It means we keep this function zi root 3, we keep it cubic. And then we multiply by 4 z cubic.
Z cubic negative
and then
minus.
We subtract z to the power of 4.
4.
And then we do this derivative
times to negative
which
3.
is going to be
negative 3.
It's going to be 3.
Oh, yes.
3, and then z plus
I square
root 3 squared. And then we divide by z plus I root 3 cubic. This one is
times
going to
2 times 2 cubic times 2
cubic, and then squared. It's going to be 6, right?
Yes.
And then we can take out z plus I, so that one dies.
Only 3, take out 3.
This one becomes 1.
And only 4.
This one becomes 4. Yeah. They are both complicated. Because if again we want to do the second derivative with this one, yeah, so let's just continue with product rule. So this is going to be f double prime of z.
12z square times z plus I square root 3 in power negative 3 plus z4 times to negative 12 times to z plus I square root 3 powered by negative 5.
Okay. Let me just confirm it with this one. It was z 4
over z plus I square root 3
z plus I square root 3.
Yes, powered by 3.
They used the quotient rule. Oh, should be x. They used the quotient rule.
We can give him for z4 times to z plus IQ square root 3 powered by negative 3. But the answer should be the same.
Yeah, the answers should be the same, but One of them could be easier than the other.
Let's check it out. Can we go down and check f double prime of z?
Okay.
We can say like that. It's 12z squared times z plus I cubic 3 negative 3. It's 1 minus z square.
The second derivative is coming to this.
Where?
This one. That is 6 z squared over x plus I root 3 powered by 5.
It doesn't look like mine. Negative 2.
Pushing through dx f over g. This should be equal to g f prime.
G prime or
Minus
gf prime
f.
minus g prime divided by
G squared.
g squared.
The quotient rule looks much simpler. The product
Okay.
rule is going to be too bulky. Okay, so we are going to have g, that is z plus I root 3 cubic, and then f prime, which is going to be 4
times 4z cubic
z cubic minus f,
minus
which is
z4
4, and then this is 3.
Negative 3. Oh no, just 3. Sorry.
Yeah, 3 plus
Times
I
z plus I square root 3 square
squared.
divided by
Then we divide this
z plus I square root of 3 powered by
6.
6.
Yeah.
Mhm.
We can try to make it simpler. So
It will be 4z cubic times z plus I square root 3 minus 3z4 divided by z plus I square root 3 powered by 4.
z plus I
Plus I square root 3 powered
powered by 4.
by 4. Mhm. So second derivative.
We can also pull out the z.
Z?
We can pull out z power 4.
Yeah. 3.
Yeah, we can pull out z power 3. So this will
Z
be
power
4.
3. is
This will
4
be-
times z plus I square root 3 minus 3z.
So it's going to look like that.
Yes.
And then we can open these up. This is 4z plus 4I root 3. So this is z cubic. This is 4z plus 4I root 3 minus 3z.
Mm-hmm.
So 4z minus 3z. It's going to be
Z.
z. And then we have z plus
Z cubed.
I root
Square
4
root 3 powered by 4.
Square root 3
Yes, 3.
powered by 4.
Mm-hmm.
Then
So
z,
now we can take the second derivative of z.
let me see whether that is what the
But
system
how we?
got.
Mm-hmm.
Z cubic, z plus. Yeah, that's what the system got.
Mm-hmm.
Yeah, z cubic and then z plus
Z plus
4i
4i.
root 3 and then z plus. Yeah, perfect.
Mm-hmm. Yes, it's a first derivative.
Yeah. So next we need to do the second derivative. F double prime of z.
Mm-hmm. 3z.
So according to the formula, we are going
Maybe
to
it's
do,
better to open brackets.
Yep.
It will be 4z cubic.
So this part is going to be equal to z to the power of 4
Z to the power 4
plus
plus 4z square root 3.
4z cubic I root 3, right?
Yes.
So
We'll have
we need to
4z.
do g. So this is z plus I root 3 powered by 4. That's the g, right?
Yes.
And then we do
And
f prime.
F, it's 4z cubic
4z cubic plus
plus
4
12z square
z square
times I times square root 3
I root 3. And
minus
then minus f.
F, it's z4 plus 4z cubic I square root 3 times
Times 4 z plus I root 3 cubic. And then it's divided by z plus I root 3 powered by 8. Right?
yes.
And then we can factor out the z plus I root 3 cubic. Actually, if this was this, let me just write the f the way it was initially.
Mm-hmm.
It was z cubic, and then you have z plus 4. Oh, it had a z plus 4i.
Z4.
Z
Okay,
plus
yeah,
4i
like
root 3 There was no need of doing that. I thought it was z plus I root 3. I thought it could also be factored out. So we factor out z plus I root 3 cubic. Let me return it. There was no need of changing it. So this is z4 plus 4z3 I root 3. So if we factor that out, then this is going to be z plus I root 3. And then this will be 4 Can we factor out the 4 here? Let it be somewhere up there.
Yes, sorry.
And then this is going to be z cubic plus
3z
squared I root 3 minus 4 z4 plus 4z cubic I root 3. And then this
and
is,
also you forgot z plus I square root 3 cubic.
I factored it out.
Oh, you forgot. Sorry.
And so
Yes.
this becomes z plus
z plus I square root 3
power
5.
So we pull out the 4. And then we open this. So if we pull out the 4, we open that. This is z. Z power 4.
Or we can just put z naught instead of z.
Or we can put z naught at this point.
Yes.
And z naught was
F double prime of z naught equals z naught is
I root 3.
square I root 3. Yes.
Z naught is I root 3.
So 4 I root 3 plus I root 3.
So this is 4 2 I root 3.
Yeah,
And then
negative negative 27. Oh no, root 3, not 27. It's also negative 9 I square root 3 plus, which is also minus
9
27 I square root 3. No, 9, right? 9. Why I always want to?
It's 27 because it's 3.
So in the first part, we need to write negative 3 I square root 3, not 9.
This part? This one?
Yes. Because this square will be 3. Because.
Oh, okay. So this would be negative 3 I root 3, right?
Yes. And negative 9. And negative 3 as well. 3, negative 3 as well. Negative 3 I root 3, negative.
This is 9.
This, yes. 9, yes, 3 times 3, yes. 9, negative 9 I square root 3 minus 4.
81.
We can.
No, 9.
Yes, 3 by 3, it will be 9, positive 9, and plus, actually minus 4 times 3, it will be 12. I
This is
times 3
z
times
cubic
3.
is going to be 3. It's
Yes,
going to be negative 3. And
yes,
then I root 3. And then I root 3 again, right?
yes.
So this is going to be negative 3 is 9 times 4, 36, right?
Mhm.
So this whole part is 36.
And it will leave with the same plus, it will be positive 36 divided by
And then this part is minus 3 minus 9.
minus 12.
12.
Mhm.
Minus 12 I root 3. And then this part is 8. 8 I root 3.
Mhm.
8 I root 3 minus 12 I root 3 minus, this is 9 plus 36. It's 45. 45 times 4, it's 180. So minus 180. So 8 minus 12 minus 4 I root 3 minus 180. And then down below
Mhm.
here we have I root 3
No,
plus
no. You need to times. You need to multiply 8I square root 3 times to negative 12I square root 3.
oh yeah,
It will be
96.
yes.
96 times 3,
96 times 3.
288.
Yes, and also we have I, which will be minus, and it's turning to positive. 288, just 288 minus 180, it will be 108. And in the denominator, we have 2I square root 3
multiplied
times,
by 5. Powered
it
by
was
5.
5. Yes, it was 5.
So it's going to be 32.
Wait, 2, 4, 16, yes, 32,
9
3, 9, 9 square root 3,
I root 3.
yes.
And then 32 times 9 is 288.
And also negative. Oh, no, it's positive, right? It's positive, sorry.
So it's going to be 108 over
Divided,
288 I square root 3. So that is that derivative. F double
could
prime.
you show me? Could you scroll down, please? I didn't. 288, we're not cancel. Okay, yes, right, I agree.
So F of Z naught equals F of I root 3 equals 108 over 288
I square root 3. Okay. It was pretty long, and we all found only one concept.
Yeah.
Maybe it's better to use his solution. I mean,
yeah, it's better. But you know, the beauty of doing it together is that if you go back to his solution, you're going to understand it.
yeah, of course, yeah, definitely.
So we are multiplying that by pi I, right?
Mm-hmm.
So if you multiply by pi I, so it's going to be 108 pi over 288 root 3.
Do we need to multiply it right now by pi I?
Yeah.
Okay, yes.
Yeah. Okay. So if we simplify this, it comes to 9/24. Which is the
Square.
same as 3 pi over 8 root 3. Okay. I'm just hoping and praying that that's the answer.
Let's check it out.
So he did a D2 that. By I that he didn't do it, did he? He didn't.
No,
he just left
didn't.
you to do it. It's pi I, second derivative Z4. And then he told you that you're going to do the same thing for the first curve, the second curve, add the two integrals, and that's it. So I will leave you to do the second one as well. So we've done it around C1.
Okay, yes.
Yeah. So find your homework.
Yeah, I'll do the C2.
Yeah. Integrate around C2. Yeah, there you go. So something else is doing. This is the Laplace equation.
Yes.
It's just trying to show that for analytic functions, the Laplace equation has to hold. So Fz is analytic, so the Laplace equation has to hold for analytic function. It's like one more condition. So we say that U and V, they are harmonic functions if they satisfy the Laplace equation. Okay, and I guess that's the end of that page.
Let's move to the next lecture, right? Could you give me a sec, okay, Steven? I'll be back in a second.
Okay.
Thanks. Steven?
Yes, welcome.
Yeah, thanks.
Okay, I guess that's well understood. 10b was quite interesting. Yeah, so we go to 11, right? This is 11b. Do you have 11a?
No, yeah, 11a in a scroll up.
Oh, okay. So a recap on Cauchy integral formulas. So if Fz is analytic, this was Cauchy's integral formula, but it only works for a simple pole. But now, if we are having a function that is a pole of order n plus 1, then we use this integral formula.
Okay, remember.
So that one, under the same conditions, this integral will always be 0 if the function is analytic. And then this is an example.
The last what we read.
Yeah. Did we do this? I don't think we did.
No, I mean the same method
Yeah.
when he has two contours. I meant that.
Yeah. Okay.
Yeah, we can do it if you.
So this one looks simple. We can just do it quickly. Oh, it's a function. What does he want? He's just defining poles. This one says that we are going to have a pole at z equals -1, and it's going to be
Which
a
is
pole
1.
of order 2, right? So this function has z equals 1. This is a pole of order 1. It's simple.
Yes.
But now at z equals -1, it's going to be a pole of order 2. Okay. So for this function, if we want to find its integral along C1.
How he found that the pole of order 2? He means that the square. Oh yeah, I get it. When we perceive. Okay, no, never mind.
Okay. So let's try to find the integral for f of z. But now we are going to integrate it around -1, right? So this is going to be integral 1 over z minus 1 divided by z plus 1 squared, right? And then if we go back up to this Cauchy's integral formula, we are going to find out that this is going to be equal to 2 pi I. So n plus 1 is 2. So n factorial will just be 1. So that remains as 2 pi I. And then we will only need to do the first differentiation of fz. So d 1 over z minus 1 dz. Okay, but we have to equate z to z equals -1. So this is going to be
z naught equals -1, right?
Yeah, z naught equals -1. So z minus 1 powered by -1, it's going to be -1 over z minus 1 squared, right? So if we replace that with -1, we are going to get -1 over -1 minus 1, -2. -2 squared is 4. So this integral at C1, it's going to be equal to negative 2 pi I over 4, which is going to be negative pi I over 2.
Over 2.
Yeah.
Mhm.
And then let's do the same integral around C2. So this is going to be 1 over Z plus 1 squared over Z minus 1 dz. But now in this case, we are going to use Cauchy's formula.
Mhm.
So it's going to be
2 pi
2 pi
I
I
divided.
multiplied by f of z naught. So multiplied by 1 over 1 plus 1 is 2. And then 2 squared is 4, right? So this is going to be 2 pi I over 4 gives you pi I
over 2.
gives you pi I over 2. So pi I over 2.
And
If you add the two integrals, you get
0.
0. So the integral around for that curve, it's going to be 0. Okay, so they got negative pi I over 2, then that integral became 0. What does that mean? So we found the integral is 0 and the function was not entirely analytic.
Okay, then
Yeah,
the contour of C, the integral of contour C is equals 0.
yeah. So
Why
that
he provides this information? Even if it's not analytic, it can be 0. That's
Yeah.
what he meant.
So G of Z is analytic at every point inside C1. Okay. Oh, G of Z is analytic, that's true. So he's trying to show that this function is not entire. It's not entirely analytic, but we have found that its integral is 0. So it only means that we can have a function that is analytic and the integral happens to be 0 as well. Okay. Yeah. All right. Next is Morella's theorem. I don't know who that is.
Morella's.
Yeah, there are many mathematicians, but this one is new. So the integral around the curve C for f of z dz, it's 0. So this does not mean, oh, so that is what he wanted to say. You see what we just found out? Remember,
analytic.
There was a theorem by Cauchy and somebody else.
Okay.
It was Cauchy and somebody else, starting with a G, something like that.
So,
so these two people said that if Fz is analytic, then the integral of that analytic function will always be 0, right?
Yes.
But now the question is the converse true? You ask yourself, if the function, if the integral is 0, does it mean it's analytic? But now, in this example, we found an analytic function whose integral is 0.
0, yes.
Yeah, and this example supports Morella's theorem, who said that if a function, if the integral of a function around a contour is 0, then f of z must not be analytic. So the converse is not true.
Oh, really? Wait a second. Okay.
So one implies the other doesn't imply the other.
So when we say that integral of f of z equals 0, it means that the function f of z is analytic, right?
No. When the function is analytic, the integral is 0.
Is 0, yes.
But when the integral is 0, the function must not be analytic. It can be analytic or fail to be analytic.
Okay.
Okay.
Let me write it very quick. Okay.
Yeah. So
when integral equals 0, then it means that function f of z is not, you said, is not analytic.
Need not be analytic, must not be analytic. That is, it can be analytic or fail to be analytic.
Not be analytic. Okay.
Yeah.
Okay.
So the name is Kachi Gosat.
Something like that.
Yeah. So Kachi and Gosat said it one way, but Morera said going back is not true. The converse is not true.
Mm-hmm.
Sequences and series on complex numbers.
Oh, yeah. He's moving to the series.
Yeah.
And sequences.
Maybe it's going to bring about Taylor series, Maclaurin series. We have other series, we call them Lorentz series. Okay. At what point do we go to the homeworks?
Maybe later. Let's finish maybe with this one, or you need to take a.
No, we can just finish. Yeah.
No, I mean, can we talk about sequences and series today?
Yes, we can. Okay, so
maybe just started. Too.
So a sequence Zn is function from a domain which is the set of real positive integers to a subset of points in the complex Z-plane. We assign to each integer 1, 2, 3, 4, blah, blah, blah. So the integer is going to be assigned a point in the Z-plane. And we have that complex number. And this is an example of a sequence. So 1 is going to be assigned 1 plus I, 2 is assigned a 0, 3 is assigned 1 minus I, 4 is assigned 2. So this is an example of a complex valued sequence. If the limit for this sequence as n tends to 0 is a constant, that is a fixed complex number, then we say that this sequence Zn converges to L. Okay. For every epsilon you give me, so this is the definition of continuity. I think
give
it's
me
trying.
A sec.
Okay.
What point are you talking about right now?
Oh, I'm talking about this point. We are done with that.
Point converges to L.
Yeah, the definition of a sequence converging to a complex number L. So this is the definition of continuity. So for every epsilon you give me, I will find an integer n such that the magnitude of Zn minus L will be less than epsilon whenever n is greater than n. So this is trying to show that the sequence is going to be continuous. i.e. all but a finite number of points are going to be within the epsilon neighborhood of L.
I didn't get the last. For every epsilon you give me, I will find an integer n such that Cn minus L less than epsilon whenever n such that all but a finite number of points.
Can I use
yeah.
a sequence of real numbers to illustrate this?
Yes, of course.
I beg not to use a sequence of complex numbers because it's going to be complex. So let me use this sequence. Look at coming from 8. 4. 2. The next one is 1, right?
1. 104.
1, 4. And it's going to keep going, right?
Yes.
Do you think it's converging? It's going to definitely converge at some point.
Converging with what?
To converge is to get to some point where the numbers stops showing up. It stops.
No, it's not converging. I don't think so. Let's stop. I mean, like, there's no any information. We need to any inputs to think about it. In this case, we can start from. Oh, you mean to the down? Yeah, it will converge.
To which number?
It's a really small number.
Okay.
1 over, now we will tell that 116. No, not 116, 18. 116, 132, 164, and blah, 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 blah. Go away. Maybe 0.
Very good.
Like,
it's going to converge to 0.
Mm-hmm.
It converges to 0. So 0 is like your L.
Okay.
So it will get to some point, and then every number will be 0, 0. Every number that comes after it, it's going to be 0.
Okay.
Because once it converges, you cannot get a number below that. So you're going to keep getting the same number, right?
Mm-hmm. Okay, yes.
So if I use 0 as my L, then we want to define what we call an epsilon neighborhood of L. So we are going to say that if you pick, this sequence, I'm calling it, maybe I could call it AN, right? Where this is A1, right? The 4 becomes A2, the 2 becomes A3, the 1 becomes A4. Okay, so it's going to converge at some point, which we are calling AN. Okay. And that is why we are saying that if I take some n that is larger than an integer n, the point that it's going to start converging is the one we are calling n.
Okay.
Because
for every epsilon,
it will get to a point and get so close to 0.
Yes.
And then every other number beyond that point is going to be in the neighborhood of 0. Numbers will get so close to 0. They will get into the neighborhood of 0.
What is the epsilon?
Epsilon? Epsilon is a number. It's like the distance. So epsilon says that the distance between my numbers, my sequence Z, and the number where it converges to, it's going to be a distance epsilon, right? So it's going to be very small, less than less than epsilon. So epsilon is a very small distance. So in short, the statement is saying that the numbers are going to get so close to L. It's just trying to define what we mean by convergence. Yeah.
Okay. 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 And okay. I think I understand.
It's quite abstract.
Okay. Sequence. Okay. What about series? Okay.
So a series, so a sequence, for example, if I give you 2, 4, 6, 8, this is a sequence, right?
Yes.
So a series happens when you add them. 2 plus 4 plus 6 plus 8. The sum of terms in a series is what we call, in a sequence is what we call a series. So the series for this sequence, this simple sequence, is going to be
summation
20. Yeah. So the series is the summation. The sequence is the list of elements.
Okay.
So if a sequence is not convergent, we say that the sequence is divergent.
If a sequence is not convergent, okay.
And this is an example of a divergent sequence. It's not heading somewhere. It has no direction. So 1 plus in is divergent. Therefore, the point, the first 4 terms keep repeating endlessly. So it has no direction. It will keep repeating itself.
Okay, I understand.
Yeah, 1 plus
Like
I0,
this one.
1 minus I2, 1 plus I0, 1 minus I2. It's going nowhere. It's
Each force,
yeah.
Each fifth position is repeating. Okay.
Yeah. Can you show that? So there is this sequence. This one is converging to 0, right?
I don't see your cursor.
Oh, you can see it now.
Okay, yes.
So there is this sequence 1 powered by n plus, is that 1? Yeah, plus 1.
It's 1.
Divided by n. It's converging. And for us to see that it's converging, we can do I. The first term is going to be n is 1. So this is I squared.
I squared, I cubed.
So it's going to be I squared, which is -1. And then this one is going to be I cubed over
3.
Over
2.
2.
Sorry. Over
right?
2, yes.
I powered by 4 divided by 3.
Yes.
So we are saying that it's converging because once
it's
it
going
gets
to 0.
Yeah, once these numbers become very big, like infinity, whatever number we have here, it's going to approach 0.
Yes, we can count that is almost 0.
Yeah.
We can assume.
So it's going to go so close to 0. So here's another sequence.
Okay, he's showing us in this graphic that is going to 0. Okay,
Yeah.
understand.
That's a nice graph.
Yeah. Nice plot, really.
Next, we have 3 plus ni divided by n plus 2 ni. So I can see what he did. Oh, he wants to check whether this is converging.
Okay. How we can check if it's converging or not?
So the formula is to do a limit. The limit as n tends to infinity, you compute that limit.
This one is going also to 0 because n is going to 0. Oh, to infinite, right? To the infinite number.
Is this 2 pi I or is it 2 ni?
It's 2 ni, n.
So this is going to be I divided by 1 plus
No, plus
2i.
2.
It's going to converge to this. I used L'Hopital's rule. I did the derivative. You see, remember L'Hopital's rule? I just wanted to avoid this way of doing it.
Yes.
You see, you needed to do limit n approaches 0. This is 3 plus ni divided by n plus 2ni. You see the derivative limit n approaches 0. This is I. This is 1 plus 2i. And so the answer is going to be I over 1 plus 2i. So it's going to approach that number. I don't know whether that's what he gets. Converges to, this is 2 over 5 plus I over 5. Two over 5 plus. Okay, it's the same thing. Let me see. Why don't we multiply this by 1 minus 2i to rationalize the denominator? Multiply this by 1 minus 2i. It's going to be I plus 2, right?
I minus 2. Yes, I plus 2. Sorry.
I plus 2, and then here we got 1 plus 4. It's 5. So I over 5 plus 2 over 5. So this is the same as this one. We just rationalized the denominator. Yeah. L'Hopital's rule is easier compared to all this work. So an infinite series or series of complex numbers, that's the infinite series. It's called convergent if the sequence of its partial.
An infinite series.
I think this is terms. If the sequence of its partial sums, the word is sums, converges to some fixed complex number L.
And an infinite series of complex numbers is called convergent if the sequence of its partial sums converges to some fixed complex numbers L.
So S1 equals, you know what we mean by partial sums?
No, partial sums, it means that we are adding to the previous one. I mean, like what's he showing, like Z1 when S2 it equals 2 previous, and S3 it will be Z1 plus Z2 plus Z3. It means the partial sums, right?
Yeah. So we have a theorem by Leibniz. It says that dz dx of the else notation. Oh. Okay. Dz dx of the else notation. We can skip that. I am not able to tie in this information with what we are talking about.
Let's keep this one.
Let's keep that one. Okay. So a geometric series, it's a series that grows using a common ratio. A simple example, if you think of 2 and then 4 and then 8 and then 16, you see we are multiplying by a constant 2 at every step, right? So if we are talking about a geometric
It's like
series,
geometric progression.
yeah, you're familiar with that?
Yes.
So for a complex number, this is how we define the geometric series. We're going to have a plus az plus az squared plus az powered by n minus 1, and it's going to keep going. So a is called a constant complex. And then for this series, we define its summation using this formula.
So geometric series, we found, okay, the summation of a is a constant. Sn equals a. Okay. Okay, we use this formula to find partial summation, right? Or
we use it to find, yeah, we can use it to find partial summations. Yeah. Let me just show you where it comes from. You know, if we start from some point A, and then we multiply at every step, we multiply by a constant Z. You know, the number that follows A, it's going to be AZ, right? And then the number that comes after that, it's going to be
AZ squared.
AZ squared. And it's going to keep going
AZ
up
cube.
to AZN.
Infinite. Yes.
Right? So this sum, we want to know what will be the sum. So we do A plus AZ plus AZ squared all the way up to AZN, right? And we can write this sum and say we are summing from n starts from 0 and
to go n.
It stops at n, and every term is a n starts from 1. It starts from 1 and it goes to n minus 1, and this is going to be a times z
divided, a times z
powered by n minus 1. Right?
Okay.
So this is the sum that we are calling as n. Okay. Let's multiply everything by z. So let's multiply this by z. Z multiplied by Sn. So it's going to be a times z. The a will become az, right? The az becomes
az squared.
Az
squared, az cube.
Az cube.
Az n plus 1.
And then this will be az
n plus 1.
N plus 1. Right?
Yes.
This one stops at n minus 1. So
it should be.
So this one is going to be
just n. Yes.
Yeah. What if we decide to subtract z as n? We decide to subtract Sn from it. So it means we are going to do az minus, we are going to do these terms minus the terms above, right?
It will be only
So it's going to be
a plus azn. A minus
to be a minus azn, and I guess you just did the
no,
other way
actually
around.
not minus in this case. It will be plus. because HZN it's a part of Z times Sn. Z times Sn is
It's going to
greater
be,
than.
okay, we are doing the top, right?
Okay, top
Minus
minus
the bottom.
CSN. Yeah, in this
So-
case will be,
We are going to have A, and then
Mhm.
this cancel,
yes,
all this, they
agree.
cancel out, right?
Mhm.
And then this one cancels with some AZ power n minus 1, but this is left behind. But you see, we are doing,
Mhm.
we are subtracting the top minus the bottom. So we are
Yes, I
going,
agree.
so it's going to
A-
be minus AZN.
AZN, yes. In this case, yes, right. That's
So
correct.
if you factor out Sn, you get 1 minus Z
Mhm.
equals A, and then 1 minus Z
1
power
in
n.
ZN. Mhm.
If you divide, you get Sn equals A 1 minus Z to the n divided by 1 minus Z, right?
Mhm.
If you multiply top and bottom by -1, you can also say that Sn equals A Z to the n minus 1 divided by Z minus 1. So these are the two formulas that give us the sum of n terms in a sequence, in a geometric sequence.
Mhm.
So yeah, so that's how they were created.
Yeah, and you prove the formula.
Yeah, that's what we were doing. We were just proving it. And this is what he did.
Mhm.
Yeah. Okay, so when Z is less than 1, the sum to infinity becomes this. You know why?
Because we don't need to count n in this case. I mean, like n is going infinite, and it means that
You see, if we pick it up from here, we have A 1 minus Z to the n.
we can say that the n it's equals 0.
Yeah, it's going to equal 0.
Yes, because it's going it's going to infinite number.
It's becoming
It's
smaller and
going
smaller.
to, yes, it's a small. It's going too small. I mean, like, because n is it's a power,
Yeah.
and z as the number is going smaller and smaller, and it's getting too close to 0. That's why we don't need to count it, and we can say that it's only a divided by 1 minus z.
Yeah.
Let me make this note for g less than 1. Increment of s n. Okay. Special series. What's a
Yeah.
special series? Important.
Actually, it's not special. I think we could call it a simple one.
Okay.
So it's a series whereby the constant is 1. If a geometric series starts from 1, we can think of it as some simple series.
Mm-hmm. Okay.
Because the sum is going to be 1. The A is 1. So this is going to be
1
Zn minus 1 divided by
z
minus 1.
minus 1.
Or we could say 1 minus Zn divided by 1 minus Z. But now, if Z
Why
is
are we
less
using
than,
different formulas? Why we sometimes we say it depends on the limit,
it
right?
depends on the value of Z. So this one is used when Z is less than 1.
Okay. Mm-hmm.
And then this one is used when Z is greater than 1.
Mm-hmm.
Yeah. So
Okay, got it.
for the second one, if Z is less than 1, realize that when this approaches infinity, when n is infinity, the Zn becomes a 0. And so the Sn becomes 1 over 1 minus Z. And that is what we have there.
Mm-hmm.
Yeah. So
Okay.
it converges for z less than 1.
Okay.
We also have another series. This is 1/1 plus z. It's going to converge when z is less than 1. So these two are special series. Okay.
Or how you said it's simple.
Yeah, or simple basic series.
I think we can stop here
Mm-hmm.
because it's I think convergent geometric series. I think it's getting harder, and maybe we can move to the homework. Or there's only I need help only with first part, how to find
Which homework?
where homework 4.
Oh, homework.
It wasn't. Yes. It's right here.
Homework 4.
Mm-hmm.
I'm trying to open our SVD reference material because I know we are going to use it somewhere.
Mm-hmm.
Yeah, this one. Okay. And then homework 4.